Olá, pessoal, tudo bem? É, Deixa eu parar meu telefone aqui. Então, hoje, pessoal, o John Otto vai apresentar para a gente, só que ele vai apresentar em inglês, ok? Então, eu vou mudar para inglês para fazer a apresentação dele e aí ele começa a falar para vocês. Senão ele não vai entender o que eu estou apresentando. Então, vamos para inglês. Okay, now in English, it's a pleasure to have Professor John Otto Fossum here. So he's from MTNU, so it's a new region, uh, technical university. Correct me if I'm wrong. So John is a full professor there. So he has his PhD also at the MTNU. So and he's a very experienced researcher. So he has more than 130 published papers. In the last 15 years, he has supervised 14 PhD students. If I'm wrong, I got from the TV, but if I'm wrong, you can just say to me. And 50 master students. And also, he has a lot of citations, so he's a very renowned scientist. And today, he will be talking to us about explain some other things about food science. So, John, we just have a gift for you, a reminder of Ilum. So, yeah, you have some things there. Thank you. So, John, the word is yours. Thank you a lot for coming to Ilum.
Okay, this is working. Fine. Yes. And I wish you advice to stand over here. Okay, I'm standing in the right place. Okay, so as you said, I come from here. This is too loud. Like this. Okay. Okay, I come from Norway. You may know where is Norway. It's here in the north of Europe. I come from a city called Trondheim. It looks like this. This is the old downtown, the Vikings, if you live here. So this is the Viking capital of Norway, 1,000 years ago. And now it's the university campus is here. This is the Norwegian fjord. We have heard about the Norwegian fjord, which is in Atlantic. And then now it's not the capital of Norway. It's the third largest city in Norway. And it has to have, in Norway, it's a big city. In Brazil, it's a very small city. Because in Norway, there are only 5 million people. And this city has 320,000 people. But 20% of them are students, because this is the only university in Norway with a focus on science and technology. We have all disciplines in the university, but we have science and technology. Yeah. And so 20% of the population are students, which means that the student life is very active. We have many places for students to go out and work. The university actually guarantees the head of Oslo, in the metro in Oslo, the capital of Norway, where they advertise that they could guarantee that students would find a girlfriend or a boyfriend if they come from there. Okay, so this is it. What am I doing now? This is only okay. So my research group, we have a lab there. It's called soft and complex matter lab. It's very little bit to do that. So we have some equipment. You see, it looks a little bit like the labs around here. That's our research group. In addition, it's also similar to here that we use common equipment. We are associated with the NANO laboratory, which is common equipment for many groups in the university. And we go there, we have to pay a little, and we can use that equipment. In addition to the equipment we have in our own lab. In our group, in addition to these two lab facilities, we go a lot to synchrotron energy sources. For example, we go often to France, European synchrotron radiation facility, which like this. There is also a neutron facility, not HQ. We go often to UK. There is a efficiency food and a nutrient facility. We go often to Sweden. There is a nutrient farm, and we are in the process of building a nutrient facility there, European installation site, and we come here, in fact. Our group actually was the, I think it was the most frequent overseas user of the old secret code. Our group, I've been coming here for 20 years, and we came here like 2-3 weeks every year with people in Norway and collaborating with groups in Belgium. So we did lots of experiments in the old secret code. We have never done experiments here. But really, in our group, we collaborate with many institutions throughout the world. And these are the logos of the places where we collaborate. And they are located here, as you can see. What it means that these dots are around, it means that I travel a lot. So that's so now I'm here. This is our group. It's not enormously big, but this is our group consisting of some professors, some postdocs, some PhD students, and some master students, and some guest researchers. Many of these people are from Brazil, like this guy. Who else is from Brazil here? So this guy, and we have over the years, I have picked a house, 5-6 Brazilian people. So that's what we do in our lab. We study natural materials. So we do material science or naturally occurring nanomaterials. And what can go to can be minerals, it can be biomaterials extracted from plants, and etc. And other types of different materials. So more like not organic, inorganic, or not live materials. But what they have in common is that they are sustainable. They don't cost much because we can take them directly from nature. We don't have to synthesize them. They are typically non-toxic just because they are part of nature itself, the first place, and also for the same reason they are environmentally friendly. So all this research is maybe, it has many motivations, but the main one is sustainability. It means that the materials are recyclable, or it could be an ore here, or renewable. So this is just to illustrate that motivation is to replace existing materials with new materials that we already find in nature that are renewable or recyclable. This is a plot showing how long time, so if you throw material into the ocean, how long time does it take before it disappears? So we want to make new materials which can actually go back to nature faster and don't pollute. So our funding in our group comes from two sources. It comes from the Research Council of Norway. We had also had some funding from Brazil, CNPP in the past, but now these days it comes from the Research Council of Norway, but also from the European Union. And there we have a large European project, which is called PICFood, which is picturing emulsions, for food applications. What does that mean? It's I assume you don't know what is a pickling emulsion. So what is it? You know what is an emulsion? Who knows what is an emulsion? I know what an emulsion, so I can raise my hand. Yeah, okay. An emulsion is a droplet of one material embedded in another material. It's a continuous phase, and then you have droplets of another phase in that phase. So it typically can be oil and water, oil droplets in water, or water droplets in oil. Or it can be oil droplets in oil, if the oils do not mix. So if you do that, if you make oil droplets in water and you wait, you will get phase separation. The oil goes to the top and the water stays below. If you want to make food out of this, milk is an example of emulsion, mayonnaise or this kind of material. In order to prevent this separation, it happens automatically in the fridge. If you wait long enough, sometimes you see it in the milk. But if you want to prevent that and extend the lifetime of the food, you need to protect the droplets from one another. You need to poke them with something so they don't coalesce and do not face separate. So the traditional way of protecting droplets from one another is to coat them with soap molecules, surfactants. So you put surfactants on them, and then you prevent them from coalescing, and you prevent this phase separation. Another way of protecting droplets is to put particles on that interface. On the droplets, so you have many droplets, each of them are covered with particles, and then they don't coalesce. It stays stable, and you keep the mountain stable for a long time. That is called the Pickering emulsion. And Pickering, because it's named after the guy who actually studied this the first time about 100 years ago. So Pickering emulsions are emulsions stabilized with particles on the interface. So the issues we are addressing in this project is what we make is we can play with the nutritional contents of the ingredients, the oils, and the particles. And we can stabilize, we think we can stabilize, the aim to stabilize this emulsion for a longer time than existing products, for less food waste, lower costs, etc. So this is the aim of this project. In this project, we have 15 PhDs, and they work all over the world. So in our group, we are responsible for 5 of those, but those 5 also go around the world. The other 10 are placed in universities in Europe, Denmark, Sweden, England, Spain, Switzerland, Finland, many countries. They go Netherlands, those PhD things they work. And then, so this is a network where the PhDs will speak, talk physically, and on Zoom every week, and discuss their progress and their problems. And they have one thing in common, which is that they study these kinds of emulsions. So each PhD candidate then has a grant for 3 years. It can be extended by one year in some cases. So inside this project, I am responsible for 2 PhD students. I'm the main supervisor for 2, and there are these 2. So this guy is Bruno. He gets a double degree. He gets a physics degree from University of Norway, and he gets a chemical engineering degree from INCA. So he gets 2 PhDs for 1 attachment. So lucky guy. So he is here now. He's 3 years in Norway, 1 year here, and then 1 year in Norway, and then to complete his PhD. He's very lucky because he has Norwegian salary rather than here. He's rich. So, the other PhD student I'm responsible for, and this is Namra. She's from India, and her workplace is in Africa, in Tanzania. But she gets a PhD from Norway, in me. So she spends 3 years in Africa and 1 year in Norway to complete her PhD. So that means that I travel to Africa to super week. So that I'm lucky too. So then I know to see here, she sent me this picture of herself like a few days ago. And this is that she had the first experience in her life of Aurora Borealis. So this is a real, it's just outside our lab in Norway. It happens. So another type of material that we have activity on in our group at the moment is because we have a guest professor from Lisboa in Portugal. He is studying cellulose, nanocellulose, and how that kind of nanocellulose can be translated into macroscopic behaviors in plants. He observed how plants, how the shapes they form, how they behave dynamically, and so on, and try to understand that in terms of the nanostructure in the cellulose. So, and she is an honorary professor working in my group. She's called an on-site professor. And I assume many of you have never heard about Onsage, so many of you have. Onsage, he was a student at our university many years ago. He got the Nobel Prize in chemistry. He was a professor of, no, he was a, yeah, he got the Nobel Prize in chemistry, he was a professor of physics, and he got a PhD in mathematics. So he was a rather interesting guy. but he died like 50 years ago. But his name appears in basic physics books. There are many things that unsolved with 2050. So now I mentioned the food and the cellulose. Now for the rest of the talk, I'll talk about mud. And everybody knows what is mud. Right? So mud is soft. It can be sticky. It can be slippery. It can be it's liquid and solid at the same time. You can walk on mud, but you can also pour it out. There can be avalanches. So it's the kind of material that can be a liquid and solid at the same time. It is called soft matter. So what is behind this behavior? So also this mud can also be soft in the processing. You can make a race out of this. Then you can burn it, fire it, and it becomes hard. It can be soft in the processing and hard in the use. These soft materials often are like this. Polymers, for example, they can be soft when you form them, shape them, but when you use them, they can be hard. So what is behind all this is nanostructures, nanoparticles, nanoscale interactions, and nanoscale self-assembly. That is what is guiding and governing what you see in terms of, in this case, that they are soft, sticky, slippery, soft in processing, hard in use, liquid and solid at the same time. Behind there is this. So what we try to do in our group is to understand those behaviors that we see on our scale in terms of nanoscale, so particles, structures, interactions, and self-assembly. So that's basically a summary of what we do in the NOV in our group, or the play. And what this other professor can look for with the cellulose, which is same type of approach. So when it comes to clays, they have been around for some time, and they are very stable. That means that they have been around for millions of years, and they are stable. So that is one characteristic of the clay materials that you may often not find in synthetic materials. Some synthetic materials can be unstable. Clays have been proven to be stable. It may not be a coincidence that just after the clays appeared on Earth, the simple life forms appeared, simplest life forms. There are some people working on this possibility that clay minerals are the catalysts for the origin of life. I won't say much about that in this talk. Human beings have been using clays for a long time. And these are some examples of uses. Some of them may be surprising, and some of them may not be surprising. This you know. There is lots of clay used in cosmetics, in household products, in paints, toothpaste, chocolate. These uses have to do with clay particles that are added to some material to change the flow property. Like, for example, the paint, you want it to be easy to apply to the wall, but you want it to stick to the wall when you have finished the paint. So this is, so that in terms of rheology, it means that you want to tune the yield stress point, the point where it starts to flow. And that you can fine-tune by adding clay particles. Same thing with the toothpaste. So these materials, they have the same thing in common, as I mentioned. They can be liquid and solid at the same time. Like water is not solid and liquid at the same time. It actually could be. If you can time scale, if you hit water very hard, it's sticky. You die if you hit it very hard. If you jump in far above. Anyway, here it's clays are used in oil recovery. They are used for nuclear waste storage. This is a big business of use of clay. Here they are used as absorbents. Clays can absorb clay. This is the toilet. So they are so very good absorbents. This behind me, there is a product called Nectar that you can get in the pharmacies in Europe. It's pure clay pills that people give to their babies when they have stomach problems. So clay can be eaten, it can be edible, and it can do good things in your stomach. So clay, they come in two types. They come as non-swelling clays and swelling clays. Here in this talk, I'm going to talk about this. The non-swelling clays are the ones that are used to make porcelain. The swelling clays have this, go for the examples I showed. This is the absorbing property, and this is the rheological property, where you fine-tune the rheology of the material. So clay minerals, they are sustainable because they are abundant, they are stable, they are easily mined, they are recyclable, they are low cost and non-toxic. And what is important for what I'm going to talk about is that they are straightforward to functionalize on the nanoscale. We can do nanoscale functionalization, which opens for a wide range of applications. If I go back to these applications, there is usually no nanoscale thinking or any science behind this. This is empirical, not scientifically based, applications based and based. Most of this. It's because this is based on where somebody tried to mix clay into something and it worked, and then they mixed a little bit more or a little bit less, and it worked a little bit better, and so on. So this is all empirical. It's not based on science. This, what we are trying to do is to look more closely at the nanoscale to improve either what already exists for applications or come up with new ones based on functionalization on the nanoscale. Control the nanoscale, then you control our scale. So clays, they are two-dimensional materials. It's an example of two-dimensional materials, like, graphene is a very famous two-dimensional material. Clay is another two-dimensional material. And that three-dimensionality, it manifests itself on many scales. This is at a meter scale, centimeter scale, and nanoscale. This is an electron microscope image of a clay particle. And you can see that it consists of sheets that are stacked on top of one another. So clays, all clays are like this. All clay minerals that you find in nature, or synthetic ones, they can also be synthesized. They have this three-dimensional character, which is very important for their use and for how they function in nature or industry. So clays typically come from a mine or from a production facility as a powder. This powder consists of grains, flat grains, and each grain is a deck of cards. And each card in this stack is 1 nanometer thick. So it can be from micrometers to centimeters in this direction, but the thickness of each card is a nanometer. Each card, 1 nanometer thick card here, is a single crystal. So it's a flat single crystal. If you can identify in X-ray diffraction, you can identify this structure. And look, this thing, some clays have different names, but they all have the same structure. The fact that they have different names comes from the metals that are here in the middle, because this is oxygen and silicon, octahedra, and then the tetrahedra. This is octahedra, this is tetrahedra. There are silicon, oxygen, tetrahedra here, and then the octahedra in the middle. And there are different metals here that define the name of the clay. Names can be modulinite or bentonite or vermiculite, or there are many names, but the only difference between them is what we have here in the middle. Each of these cards has a charge. Negative surface charge and a very small positive edge charge. But in order for this sample not to be electrically charged, you need to neutralize this surface charge, and that is done by putting a cation here. So in between each card in the stack, there is a cation, or many cations to neutralize the charge. There is a charge density on the surface. Am I speaking too fast, or am I, and if you are in doubt about something, you can ask me question anytime.
Se quiser
Any
perguntar em
questions?
português, eu traduzo, pessoal.
I just want to make sure that I understood what clay is made of.
Yeah.
So it's kind of mandatory to have those elements and a metallic interlayer, or not every clay has this metallic interlayer.
All the clays are like this. All the swelling clays I'm
Okay.
talking about are like this. So there is a cation here. It has to be there because of this charge. This layer here in the middle are also, yeah, this cannot be touched. This can be touched, so we can change it easily ourselves in the laboratory. When I said we can functionalize it on the nanoscale, it's about changing this. This here is fixed. It's okay. So there is a difference between the middle, okay, those black dots here, that distinguishes the different types of thread. Other questions? I can talk slower if you want to. Yeah. So actually, what I just said was that the interesting thing what happens is in this layer here. Here, in between. Actually, it's more interesting what happens in between than what happens inside the card. That's what we have done recently, together with some people in Sao Paulo, is we have measured and calculated what is called the electronic band gap of the card, each card. And what we have found is that they are the most insulating materials, electronically insulating materials on the nanoscale. So this means that they have a potential for being used in, say, nanoscale electronic devices, because they are more insulating than any other nanometric material that we can find. So that's why this paper has, this publication has been nominated to, well, it has received some very good comments, very good advertisement for our group. Another thing we can do in that, what we have done in that context, I mentioned graphene as a flat material. We can put molecules, we can remove those cations and put some charged molecules inside there instead of those cations. And we can heat up this material to 700 degrees, and then we are forming graphene in between the clay layers. So we can make graphene, clay, graphene, clay, graphene, clay. What we are going to do with that, we don't know yet, but we can do it. This is an example of basic science that we can do, and then we are looking for how to proceed with that. And of course, we can have many ideas, and we are testing them. So what happens in that interlace, that's what is interesting, that I mentioned. So these are then again the clay layers, the cation. If you expose this place powder to humid water, water will go inside here in the stack. Water will go inside between each part, and the water will enter. How much water will enter depends on the humidity around your sample. Relative humidity is RH, relative humidity. So at low humidity, there is no water inside. At some higher humidity, there is what we call one layer of water inside. The reason the water go inside here is that the water molecules, they are dipoles, like this, and they are attracted to the positive charges of those cations. So it's called hydration. So those water molecules will hydrate the cations. In the beginning, the distance between these parts increased by the size of one water molecule. So there are three water molecules associated with each cation, but there is only one layer of water molecule. So the distance here increased from here to a distance corresponding to size of one water molecule. If you increase the humidity more, the distance increases corresponding to two layers of water molecules. WL means two water layers. One WL means one water layer. So this has been studied a lot by many groups, including us. So since maybe I have to ask a question, how would you measure this distance? Any suggestion? How do you see that that is one layer of water and two layers of water? not only maybe, but it is actually. It is more than maybe. It is. Like this, right? Powder X-ray diffraction. You can do. You can put the powder, this powder, in an X-ray beam, and you get the powder diffraction. Like the powder, you get the circular diffraction. You're familiar with this, I guess. Powder X-ray diffraction, yes. So this diameter of this ring, or the radius here, decreases if this distance increases. So you see the keep moving from, then you can integrate this, and or you can also cut to here and make a one-dimensional representation of this. So with zero water, the distance is 1 nanometer. When there is 1 layer of water, the distance is 1.25 nanometer. That's because the size of the water molecule is 0.35 nanometer, 3.5 angstrom. Yeah.
In order to use PXRD, usually you have to assume that your material is post-crystalline. How do you take in account the contamination in your X-ray sample or defects from manufacturing if you are doing this?
No, actually, the synthetic rays have no contamination. The natural test we can purify. For doing an investigation, so we want to understand what's going on. In some applications, we don't care about the purification. We can use them, and we know that we can understand that the clay contributes to some property, and the impurities can get together. But if you want to do a good experiment that we can publish in papers and so on, we simply purify them, or the synthetic clays, they don't have any impurities. The purpose of studying synthetic clays in this context is mostly to understand, and then to take that knowledge and transfer it to the natural clay. Then we can make new uses in natural clays that people didn't think about before, and I'll come to that. Any other questions? It's good to have questions. Okay. So these are methods that we can use. So one thing is the distance between the platelets, showing that it's 1 layer of water or 2 layers of water. But another interesting thing to understand is the dynamics of the water. How is the water diffusing inside there, and how is it attached to those fat lines? Is there any dynamics in that? That can be done with simulations, can be studied with simulations, but the experimental techniques that we use for that is, for example, nuclear magnetic resonance spectroscopy or neutron spectroscopy. Those are the two, or it can be Raman spectroscopy. I mentioned these three techniques because we have publications in this, and I mention it now in this talk because this was done in collaboration with Brazilians. This one in Recife in Pernambuco, Federal University, and this is in many Brazilian names here, and in the neutron spectroscopy space. So I mentioned that the clays are good absorbers. These are parrots in the Amazons. And in the Peru part of the Amazons, there are cliffs of clay. And in the morning, they are covered with parrots that eat clay for breakfast. So now you can explain me why. Any good suggestions? I mentioned that, there is a product in the pharmacy in Europe, which you can buy pills and give to the babies. It's basically a similar reason. Hmm? No. No. They are good absorbers. So it means that they eat this for breakfast because then they can eat fruits for lunch, and the fruits can have poisonous seeds. So if they have clay in their stomach, they see the poison is absorbed, so they don't get stomachache in the afternoon. So they're happy. The parrots are happy the whole day. And this is something that nature invented. This is nano technology, natural nanotechnology. We have actually studied if drug capture and release with the clays. one of my Brazilian PhD students, he had that as his PhD. I just met him just before I came here. I met him in the Fossum project because now he's a professor at university. So he studied that with drug delivery with the place. You can capture them in interlayers and release them in the stomach. And that is actually the cation exchange I mentioned. We can change those cations. So natural clays typically have sodium cations there because the natural clays, they have been sedimented in soft seawater or near a river outlet of a river, then they have been sedimented. So that's why typically there is sodium there in the natural clays. And also in the synthetic clays that we have access to, typically they come with sodium. But then we can play around, we can change this. And this is very easy to do. It looks like chemistry, but it's so easy chemistry that even a physicist like me can do it. So it's not difficult. You just put your clay powder in the beaker with lots of salt with the cation that you want to be there. You stir it and you wait some time and so on, and you then, since there are so much more cations of the N type than of the sodium type, they will go there and replace them. So the M cations will get any means metal. It can be cesium or nickel or potassium or something that you want. Okay. Then you just take this and then you rinse it, do a proper rinsing, then you dry it, and then you're left with a new powder. It has the other cation, the ones you want. And it doesn't have to be cations, it can be charged molecules. So you can do this, you can put, like when I said in graphene, you don't put cations, here we put dye molecules. And that contains carbon, so when you burn it, heat it up, it forms graphene. So the importance of these cations, what cations are there? We published in this paper here. This is also the first author, is one of my former PhD students, he's from Brazil. You see all the names from Brazil here. So then what we did in this experiment, we put a clay powder in this capillary, 2 centimeters. And we have a dry end and a humid end. So we looked at water diffusion along this capillary, how water diffuses. It's important to maintain same pressure at the two sides, so we know that it's diffusion driven and not pressure driven. That's important in this type of experiment. So what we did, we have one humid end controlled by the water bath, and then dry end controlled by the silica. Then what we found, one result of this experiment is that depending on what kind of cation you put in the clay powder, it takes that controls the time it takes to diffuse through the whole thing. Because the water is absorbed in each grain and released again. So it's a dynamic process of capturing and releasing of water as it moves along. In the beginning, this is completely dry, but then humidity enters from one side and it diffuses along here. Then what we found is that if there is sodium cations, it takes 200 years to diffuse 10 meters. If you replace the sodium with lithium, it takes 28,000 years to diffuse 10 meters. So the way the water interacts with what is called interlayer cations in the grain, determine the macroscopic diffusion of water through the powder. That's why, and this is another, actually that's why it's interesting to use clays as barriers for nuclear waste storage. So in Sweden, they use this way to store nuclear waste. They put the nuclear waste in a copper canister, which they put far underneath the ground in this way, and then there is an empty space around the canister, which they fill with clay. So the clay can, if there is a leakage, nuclear waste leakage, it will be absorbed by the clay. The clay also has this property that if it gets wet, it could be, for example, the groundwater coming in from the outside, trying to attack this thing. The clays have the property that they are self-healing material. If there's a crack in the clay, they will heal themselves. So these two properties are behind using clays as barriers for nuclear waste storage. Clays are also used in as gas barrier in polymers. You know, polymers are spaghetti, or printed spaghetti. If you embed in that spaghetti clay platelets in 1 nanometer thick ones and align them, you increase the pathway for gas migration. So it will take much longer time for gas to go from one side to the other. Do you know why you cannot buy beer on a plastic box? And you said, why don't you? If you go in the bar and you buy beer, why can't you? Why is it in plastic bottles? Yeah, it has clear. The oxygen can go through those pores. That's correct. So, but if you put a tracer, you, you block those pores. Yeah. So you can store beer on plastic bottles. But there is something called consumer uh, tradition, and nobody wants to buy beer on plastic bottles. Anyway, people won't believe it. That it can be good. So, no, so how am I doing now? Usually I speak a lot. So, okay, I'm going to have to really fast because I have many things to say. So one thing they have been doing recently is actually to capture CO2 in those interlayers between the platelets in the powder. That's very interesting because, we want to capture CO2 and the whole world wants to capture CO2 now. So we wanted to investigate if the clays are good material for capturing CO2. So that's in this paper. This is also the collaboration with us and some Brazilians, and mainly we do experiments, and at the University of Sao Paulo, they do the simulation. So we published all the papers on that. And what we found is that the capture of CO2 is determined by what kind of cation you put in those interlayers. So you see here, this is a shift of the drag peak when we expose the clay powder to CO2 on the surface. So you see for two cations, lifted and diffused, the drag peak moves, meaning as the CO2 goes into the interlayer. So the other cations, nothing happens. They do not absorb CO2. What we also found is that there's another type of experiment that are doing in addition to the X-rays. We can get away the clay and expose it to CO2 and measure how much the weight increases. That is called gravimetric absorption measurements. Then we find that the clays perform as good as the best materials people use in this context. Clays are very good CO2 capture. What we are working on now is to transfer this into technology, which is not easy. But now we have the proof of concept, but then we need to convince some investors or industry or something to help us to develop this. Now we understand this, but we don't know how to get it into industry. The advantage of clays compared to the other materials is also that they are very cheap. It costs maybe $1 to $10 per kilogram, whereas the competing materials can be 50 times more expensive. And they are synthetic and not stable and they are toxic, particularly useful for moths. Again, compared to the moths are, because they are not, in terms of sustainability, not as by far not as good as it was. So this is an interesting calculation. You know how to estimate how much CO2 you can capture in a clay. Because if you have 1 cubic meter of clay, can you, if you're hide this, let me do that here. What is the surface? You have these cards that on top of one another, and each card has a surface. If you add those surfaces of all the cards, and you have 1 cubic meter of volume, what is the surface area in 1 cubic meter? So you have a base of 1 square meter, and then you have 10 to the 9 square meters on top of one another. Actually, 2 times because it's up and down surface. So actually the surface area of 1 cubic meter of clay is 2,000 square kilometers. It is a big surface. So, and then if you have one cation, actually what we know, the number of cations that are sitting in the surfaces is determined by the chart. I mentioned the charts of the chart. We have a chart per unit area. So there is about 1 cation per square nanometer. Right? So that means there are many cations in 2,000 square kilometers, which is 1 per square nanometer. So that means that if each cation captures 2 CO2 molecules, then you can have about 14% mass increase in the clay per cubic meter if it's saturated with CO2. And that's approximately what we know. So this is like waves are performing better than the other materials because the density of the pore space is so dense, and you have this enormous surface area per unit volume. No, it's not as simple as the cations capture CO2 like the cations capture water. Because the cations capture water because water is a dipole. But CO2 is a dipole. Is CO2 a dipole? No. It's straight. It's a straight molecule. It's not a dipole. So why should the cations capture CO2? And then I was thinking about this for many years. We measured that it captured CO2, but we didn't understand why. And the first thinking was that maybe the CO2 dynamically is a dipole. It can bend, and then it can be attracted to the cations in this way. But that's not what happens. What happens is actually something related to something called ordered interstratification. So in the case, when you do the cation exchange, if you look closely at the system, it actually won't change cations in every layer, it changes cations in every second layer. So that is, and this is not quite understood why. But this you only observe in synthetic clays where the chart, because here you can the negative charges of the surfaces that I mentioned. To observe this in a very homogeneous chart distribution. It can be homogeneous, there can be chart distribution in the plane, on each plate, or it can be between plates in the structure. So if this chart distribution is not uniform, you want to observe this easily. But in the synthetic case, we can. So in the synthetic case, we observe that each interlayer, every second interlayer is cation exchange when we do this process. How would you see? So this actually shows how you see it in X-rays. So can you explain this figure? You see this thing here? Actually, what happens when you exchange only every second interval is that the unit cell doubles roughly in one direction. So there is a new drag peak appearing when you do this. If it's not there before you do it, before you do the second change, you have a drag peak here. After you get a new drag peak at half the typical value in the poly diffraction. And that is because you have doubled the length of the unit cell. That's how we observe that. So what happens when the cation is with nickel? Before nickel hydroxide in the water, nickel hydroxide can have a positive charge, and that nickel hydroxide will go into every second interlayer. And what actually happens in the CO2 capture is that the CO2 is captured by those interlayers. These CO2 include this. So CO2 is captured by nickel hydroxide, not by the pure nickel. And then I will skip this. And I will now be talking about the clays as stacked, and there can be one water layer, two water layers, or CO2, but this is called crystalline swelling of the clay. It's there like the stack, but there are few layers of molecules in liquid. The other thing we can do is to expose the clay to liquid water instead of just humid air or CO2 gas or other gases. We can put it in liquid water. What happens then is that the clay circuits, clay pressure, 1 nanometer thick, separate and at a distance. And they stop at a distance when the container stops. So the container decides when the distance between the pressure. Depending on the volume percent of clay you put into the water. This you can also measure with X-rays, but then we are going to small angle scattering or ultra small angle scattering. Have you heard about small angle scattering? There is a beamline at the series, almost finished, but they are doing small angle scattering. And what we can study are these kinds of systems. Because the clay platelets, they can be randomly oriented in the water, or they can be aligned. And the alignment, so if it's dense, they don't have possibility to rotate. So they are aligned with respect to one another. If the distance is big, they can rotate freely. And so this is for an isotopic phase, this is for the non-massive phase. This is for the liquid crystalline phase. These are liquid crystals. So this is how a liquid crystalline phase for the clays would look, depending on the container. So typically, when we do experiments, we study them in a cylindrical capillary tube, and they will align with the walls. So they will be their pressure will be standing up in the suspension. So if you look from above, the suspension will look like this. If you look from the side, it will look like this. So this is pneumatic ordering of the clay pressure. Here from wall anchoring. The wall anchoring is important. This we can also the clay. Another thing is that in this spindle system, the clay pressures they respond to a magnetic field, so we can align them in this. If they are in the first place aligned like this, they can be aligned further with a magnetic field. It was also done in Pernambuco years ago. Actually, many years ago. Time goes very fast. You may not have noticed yet, the time goes very fast. So the first study of clay in photonematics that I described was actually done by this guy, long years. This is an example, like depicting phase dimension of a person who studied something and then nothing happened for 50 to 100 years. And people started to work on it together. And then examples like this, it's out. Somebody did something and nothing here. We did publish this in 1938, and in 1988 or so, people started to work on this again. So when you put this place in water, I will skip this because interest of time. I will talk about this paper in the end. This is a paper we published about colors. Can we use the place to make colors? So and then so in the world there are many ways of making colors. Not so many, but a few. And we can distinguish between chemical colors or physical colors. Chemical colors are the ones, is the principle behind painting our houses and cars and clothes and whatever. And the color you see is the light that is not absorbed. It's coming back, it's what is not absorbed. That is very material dependent. It depends on the electronic orbitals and so on. So it's very material dependent. And that is actually historical and current pigment technology is based on this. But if you go to nature, this is not the most common way of getting colors. If you look at animals, from plants, insects, fishes, their color are physical colors. And that is not this mechanism. It's the same mechanism as it's in the soap bubble. It's interference. It's reflection and interference. You know, the soap bubble is almost transparent, completely transparent. But you get back reflection from the two walls, behind back wall and the front wall. Then you get enhancement of one wavelength, constructive interference, and that's what the color you see. And you see different colors in the soap bubble because you look at it from different angles when it curves. Because this principle gives angle-dependent coloration. This is the physical colors. if you look in the, for example, this butterfly wing, it has a material on the top of it that is almost transparent, but it has this Christmas tree-like structure where you get reflection from the branches and you get constructive interference. That's why you see the color on the butterfly. It's not this mechanism. It's not what the same at all. Two different ways of making color. There are other ways of making colors, which I won't go into, but I just mentioned. Refraction is what you see in the rainbow or the prism, the prism mechanism. There can be plasmonics, which is nanoparticles, the electronic oscillations in the nanoparticles and resonances. And there can be barotrain things. But I won't talk about those. I will now focus on this. So then a motivation for this is that there is an issue with pigments. The traditional pigments that are based on the chemical polarity. And the issue is that they are toxic and they're not sustainable. So this is a friend of mine, he's a chemist, now he's in Germany. He has made this block. So the issue is about toxicity, sustainability, and price. This is what so we as consumers and environmental people, we are concerned about sustainability. Industry is concerned about price, and they are also concerned about toxicity. So the pigments that are used in our clothes or our houses or cars, they are typically toxic, but they are low cost. That's why industry is using them. And they are low cost for several reasons. It's the established production protocols, and it's the price of the materials that they use for the pigments, the lining and all. Then she is working on plant-based, cellulose-based coloration. I won't have time to go into the mechanism there, but the problem with that is that they are expensive. Now, we wanted to try to see if we could make colors from place. And then, because they would be low cost, I explained already why they are low cost. They will be sustainable. I explained why they are sustainable. We can make structural colors based on place. And how would you make structural colors based on this place? And it's adjustment. No. No. If you remember the suspension, the reticulate platelets, those are interfaces. If you reflect from one layer, 1 nanometer sheet, and then you reflect from another nanometer sheet underneath, you can get constructive interference in principle. So this is what we want to investigate. We put this place here, synthetic place in this place, and we disperse them in water, and we control the volume percentage rate in the container so that the distance here would correspond to the distance for constructive interference of visible light. If we did that, we got this, which sort of gives us color, but not very impressive. So this would not be good. And the reason it's not very impressive is that this plate surface, 1 nanometer thick, are almost completely transparent. The light just gets straight. But very few things we can do. And that is this I mentioned about ordered interpretation. What we did, we put cesium ions in every second layer, and then we hydrated this because cesium doesn't hydrate with water. The sodium that are there hydrates the water. So we can separate this into double layers of water with cesium in between. And those are less transparent, they are more reflective than just the two layers. And then we get enough reflective light to get the bright color. So this works. Then there is something here which is important. There's a dark background because still the white light goes, most of the light goes straight through. So you need a dark background to observe that white light. If you don't have the dark background, you get white. You don't see any color. And so we see it when you lift these things that they are actually transparent when you lift them up. Yeah.
So you search the 79 version.
Mm-hmm.
What? Why? you control the difference between the layers.
Mm.
But nice machine by the surface on the layers once you reduce extension so that once it's dry, the distance.
This is where we are working now. So we also help us with this. You are welcome. So this is our research at the moment. So actually, this is the white. This is a white paper underneath. You pull it out and you see the color because then it's on the left background. And then if you look in the peacock, it's the same thing. The back of the peacock is black and the front is colorful because the peacock feathers are colored with intensity. That's the reason. So then we can measure we can see this is behind here is the directional law, which gives the condition for constructive interference. But you can see both first and second order reflections in direct law. So we measure the color spectra. This is not expensive instrument to buy to use. Another issue with this kind of coloration is the angle dependence. I mentioned this in the soap bubble, we see different colors because there is an angle dependence. If the system has disorder, then disorder in it, you lose some brightness, but you gain angle independence. It's called non-iridescence. And this is an issue if you want to make technology out of this. You don't want to have a house, maybe it has different colors depending on the angle. It could be fancy, it can be fun to have, but maybe not everybody wants a house like so to control that is an important factor, but this is controlled by having some disorder. This is how nature controls it as well. Remember the butterfly wing with the little Christmas wheels, it has disorder, so the color is the same from different angles. But 10% disorder typically to get this. There is one technology that uses this principle. It is a Lexus card. It has mimicked a butterfly wing in terms of nanostructure, and you get blue color based on constructive interference. The problem with this technology here is that it takes 8 months to produce sufficient pigment for 300 cars. And the point that takes time is this. This is nanolithography. It takes a long time to produce this structure. So if you can, if somebody then came up with something that could actually remove this step instead of 8 months, 10 minutes, it would be interesting to use structured power. And that's one issue, the time. The other issue is to make red color. It's not easy to make red color by structural mechanism. You look in nature, red birds are typically pigmented and blue birds are typically structurally colored. The reason it's difficult is this. This is based on work that people did on packing colloidal particles. Let's say you have a colloidal particle with a diameter that corresponds to blue interference from the top and the bottom. You get reflected to the bottom and to the top, and you get blue color from that. If you pack that kind of system very dense, you will see a structure that also gives blue color because the intensity you measure is a product of form factor, which is the factors in the particles, and the structure factor, which is the factors in the packing. So then, the product, if you have blue particles and blue packing density, you get blue color from both of those. If you pack them loosely, you can get red color from the structure factor, but you still have the blue factors from the form factors. And that will dominate, so you will always get blue, whatever you do. So then you can put this animal has resolved the problem. This is the chameleon, it's red, structurally red. And it's structurally red because it has this in the skin of the chameleon. There are these embedded little crystals, and the distance between them gives the interference. That gives the color. So what happens is that this is a male chameleon. He sees a very beautiful female chameleon over there. When he gets excited, his skin is green, he spreads his skin and he becomes red, and he gets excited. Then the female is attracted to the fancy red colors, and then this thing happens. So that can be resolved, and the way to resolve it in, in the case of so colloidal particles, if you use what's called core cell particles, they're only the distances between the core nothing. What we can do with the clays are the same because they have resolved this problem because the form factor is what just 1 nanometer. It's in the X-ray range. The structure factor is the distance between the plates. So we have resolved these two things. We can make colors very rapidly, and we can make red colors at a very dark. So our clay system has resolved all the problems associated with making technology out of the future. So then you see here, we still have to correct with the dense suspension, and then we fill the rest of the correct with just water, and we mix it and the colors appear. We use speed predictions and everything. It's just to show the principle of this is a very rapid process. Then we can go to the synchrotron and we can study what is the, we have to go to the synchrotron to understand what is the reason for the disorder in the synchrotron, to understand the non-iridescence. So that we can do with small angle scattering. Our conclusion of that is that the stacks are small domains. There is a fixed distance between the places in the domain that gives the color, and the misalignment of the domain gives non-iridescence. We skip this. There are some issues here that we can talk about X-rays, and you have to really keep the tongue straight in your mouth when you do this X-ray experiment to analyze data and know what you're doing. So for example, if you put X-rays on a capillary with this in the suspension, you only see this yellow part. The rest of the capillary you don't see. So you have to think about this when you do this problem. So the question was, how can we maintain this distance with the hard material in the field? That's where we are now. Because if you want to make pigments out of this, that's what we have to do. If now we have put this in water in the rats, can be used for painting your house, but or cosmetics, but that's where we are now. Then we can think of making flaky pigments and paint our houses. Yeah. Back to this. So I've been working on this place for 25 years. Yes.
Just a question that popped in my mind. When we think about plates, we usually think about natural plates that have that brownish reddish color.
Yeah.
That is a chemical property, or is it a physical property that
No, that is a chemical property. So, but actually, if you take them down and separate the nanoplates, they are transparent. The natural ones also. That color comes from often from iron. So let's say I worked in this place for 25 years, and our research was driven by sort of curiosity. We wanted to understand what's going on. And then when you do that kind of thing, the funding agency, like here, at this time, this was the first scientist, the funding agency was here. And then he wasn't not really interested in whether this is yellow or not, or comes up or goes down. So that's the situation for basic science everywhere in the world. And but when you do that for some time, you come up with some solutions, and then you start looking for problems. This is the very good. And then that's what we have done. We have looked for problems, the CO2 problem and the color problem. And we can use the basic knowledge that we have gathered to solve those problems. That's the idea. So this was to illustrate how important it is to do basic science without any thought what it can be used for. Then we can go back and we can improve these things, or we can make new ones like the power CO2 capture and the problem. Then we start to interact with industry. I'm a physicist, what you see, I'm a physicist. Of course, I cannot tell you everything because there are some patents and stuff involved. There are still lots of things to do down here. Before I thank you for your attention here, but I will continue. So this is some slides. I don't have time to go through them, but the train in the road of original life, that we found that quite interesting. There are some things to discuss there, but I wanted to, since I walked around here before the talk, I like the way teaching is done here. So just comment a lot in the end. So in our university, I teach three topics: soft matter science, light neutron access scattering, and something called soft technologies. And the soft technologies is like this. It's an obligatory course. So it's called expert in fields. And it's called an expert in field village. I'm responsible for one village. It has 25 students, 25 to 30 students. And I divide them into groups of say, 6 to 4, depending on how many we are. And it's intensive course. It lasts the whole January, 3 weeks, 8 to 4. I have to be there 8 to 4. It's very tiring for me and for the students, but we do this. And it's called, it's called a village. It's an expert in field village. And each group decides their own project. And in my soft technology course, they can either decide to work on soft robots or intelligent swarms. They just find out the first week what do they want to do, what kind of project they want to do, and then they work together. And then the purpose of this course is to learn how to work together in groups, interdisciplinary groups. So there are all kinds of disciplines attending this course, the students. Then we monitor them and give advice. I mean, some students come here, they can do very shy, but then they have to learn how to be shy. Some students can dominate the whole group. We cannot have any dominating. We do this together. This is the thing. So we try to guide them into this direction. And then all this facilitation goes on the whole 3 weeks, the last report. And in the end, we have to write one report about the group work, and about the project work. The intelligence work is quite interesting. It can be an example of an intelligence work is the ant colony. I mean, you shouldn't think of the ant colony as an individual. You can think of it as a whole, also entity, and it can adapt and do intelligent decisions for the whole colony. So that's an intelligence work. And we can put intelligence worms into many contexts. So at the end, we have to write a report about the project, about the group work, and each report counts 50-50, and then the group get together in the end. This is obligatory course at our university, and talking to people in Sao Paulo, maybe we could transfer this to Brazil. Are there any courses like that, like learning how to work together in groups?
We do some of that at Ilum, because we do some peer evaluation to the group, so they have to get together. Me and Daniel did a lot and so, but a dedicated course for that, I don't know.
Because there is some theory and literature and so on behind there. It has studied how people interact in groups and how you can improve that and so on. And Norwegian industry, they seem to claim that this is the thing coming from us. They are better performers when they come into industrial situation. Where they have to work in groups together with other people. So when students first come in the course in the beginning of January, some of them are very skeptical. They don't think it will be a waste of time. Then in the end, they like it.
Maybe we can discuss future plans. It's a good idea.
Okay, that's what I plan to say.
Let's thank John for the excellent talk. Perguntas, questions? Vocês podem perguntar em português, pessoal, eu traduzo, ok?
It's a simple question, but I couldn't understand what happens to the CO2 after the jet ion is captured. I'm not sure what happens, like how do you get rid of it?
Yeah. So the thing is that we need to pressurize, not high pressure, but 1, 2, 3 bars to get the CO2 to be captured by the plate. Then if you release the pressure, the CO2 comes out again.
Yeah,
So,
what,
so you can imagine that you keep the, let's say you want to use this for a filter for gas separation. It could, for example, be separating hydrogen and CO2. You run the mixture through under this pressure. You the hydrogen goes through, the CO2 stays behind. Then you can release the pressure and pump the CO2 into the ground.
oh, so you kind of get this to the ground and
Yeah. That's the plan.
a very silly question, but I just need to know how is the clay used to produce chocolate? Because I was really curious about that. Yeah, is it like synthetic clay and like about
No,
synthetic?
this is actually small amounts of clay that is used to tune the mouth feel and the flow property of the chocolate, how it melts on your tongue, this kind of thing. So it's sort of a similar effect as the usage of in cosmetics or paints or this thing. It's modified small amounts to just fine tune the chocolate process.
Um, last semester, we were working with a protein called glomalin that's found on soil.
Mhm.
And the property of this protein that was very much undesirable for many of the groups is that it has a tendency to stick to clay.
Mhm.
And you commented that there's a possibility that life started on clay particles on the ocean.
Yeah.
So have you seen any studies using biological residues to keep track of the distance between layers of clay? Or
Yeah, it works like this. We can, as I said, it doesn't have to be cation or water. This in there can be charged molecules. If you have a positive charge, they can go in there as cation. So it's all these are electrostatic interactions between molecules and clay. That can you can put whatever positively charged molecule with it has to be clay. It can be positive on one end of it. If it's a big molecule, it can be positive on one end and negative on the other, but the positive will attach to the clay.
Thank you, Professor. You have already discussed about the influence of the solvent in the layers distance, and also about the surface internalization. But I want to know more if there are influence of some physical properties like temperature of an external electric field,
Mm-hmm.
and how
So
can we use this?
this we have the work that we studies including of parameters, like how many layers of water go in, for example, whether it's one layer, two layer, or three layers, depends on two factors, basically, humidity and temperature. So that's the lower temperature, the more you can get, I mean, the higher number of layers you can get in, or higher humidity. Those two together. Then on electric fields, we have done something called, well, we can align the clay particles in electric field. Typically, what we study is in a non-polarizable fluid, because in water it won't work, because water is a polarizable liquid. But if we suspend the clay in oil, then it's electric field and align the clay in the clay. We have also done this in polymers. We have aligned, I mentioned you can use them as gas barriers. Then they have a line typically using an electric field when they are suspended in a polymer before the polymer hardens. So in the tape before we harden the polymer, we can align the electric field and harden it, and then the tape will stay aligned.
More questions? I have one. So you say the clay are the highest band gap materials supposed to be materials.
Mm-hmm.
So have you thought about applying it to insulating layers on
Yeah,
microchips?
yeah, we have
Wow.
thought a lot about.
Yeah, because it's a big challenge for the industry as the insulated layer gap.
The problem in general is actually, and one reason that silicon is so good is that we have The silicon oxide is forming naturally. The interfaces is always difficult when you work
Yeah.
with these producers. So that's where we are working now.
Yeah, but now they use hydrogen oxide already. Not with-
But I think our way of synthesizing graphene is inside is irrelevant.
Great, great. So any more questions, people? Everyone goes to the holidays, huh? So let's thank John again. So get rest, people. Goodbye.